The hydration of alkynes is going to be very similar in mechanism to the hydration of the alkenes, and it's also going to be similar to the hydrohalogenation of alkynes in some ways. So we're going to draw out the mechanism in this video. One of the differences when we're doing the hydration with alkynes is that we do add in this HgSO4, and this just helps the reaction by coordinating to this pi bond. So we don't formally show that in our mechanism, but it is good to know that you do need to add that in order for this reaction to go. We do see that we have a carbonyl as our product. Specifically, this is a ketone, and we're going to see how this comes about because it doesn't automatically look like, oh, just a double addition of water. Something else is happening here, and we're going to explain what exactly goes on. So with our H2SO4 in our water, we saw that that can make H3O+, and so we're going to write it out like that. We are going to have that same first step happen when we're grabbing that H and we're kicking off the water in this case. We're going to draw this similarly to how we did in our hydrohalogenation of our alkynes video. We saw in that video that we had to still decide which one was the more substituted carbon because that's going to get the positive. Carbon 2 is more substituted because it's attached to 3 and 1, whereas carbon 1 is only attached to carbon 2. And so we're going to put our positive charge on carbon 2, and the H is going to go to carbon 1. What's going to happen after this? We did kick out water. So this water can come back and attack just like we saw with the alkenes. That's going to make this molecule here. And now what has to happen is we do have to alleviate that charge just like we saw from the alkenes video. Once that oxygen is attached, it does have to become neutral. And so we're going to go ahead and use some more water to go and take that H off. And we'll be at this point now. What happens here, just like what happened with the hydrohalogenation reactions when we're reacting with this with HBr, we actually have 2 pi bonds in that original molecule, so we've reacted one of them fully up until this point. We still have this pi bond, though, that we do need to go and react. So we're going to start the mechanism off the exact same way. So we're going to have our H3O+, we're going to use that pi bond between 1 and 2, the only one that's left now. We're going to take that H off of the H3O+, and we're also going to be faced with another decision in terms of what side gets the H, which side gets the positive. It's going to be the same result as we had earlier. Carbon 2 is attached to 3 and 1, so it's more substituted than carbon 1, which is just attached to carbon 2. So we're going to put the positive on the more substituted carbon, which is carbon 2. That means that the H goes to carbon 1. What happens here is where the mechanism takes a turn. We normally would have this, and then we also make water as a byproduct from this. We don't actually have a second attack. So normally we'd have this part come back and attack again and just have 2 groups. What happens here is something that is a little bit easier for this molecule. So we do have these lone pairs and they're right next to this positive charge. So these lone pairs aren't going to just let that positive charge sit there and not get stabilized at all. What's going to happen is those lone pairs are going to come down to help and make a bond with carbon 2 because right now it's lacking an octet. It's very electron poor. So if we could bring those down, we can make a double bond at that position, and that's going to happen a lot faster than satisfying its octet by taking different molecule that's not part of this molecule and going to make another bond. So whenever you can do something like this within the same molecule, it's going to happen a lot faster, and that's what's going to happen here before that water would even be able to go and attack. These will come down, and that's just a resonance. That's going to make that double bond between carbon 2 and the oxygen. And at this point, the easiest thing to happen is to just take off this H, and then we're going to get a nice neutral carbonyl, which is pretty stable, and that's going to get us to that product that we have above. We've just drawn out the H's on one as we're adding them. You don't have to draw out the H's each time. We're just doing them so we can keep track. So now we can use that same water we didn't really do anything with and over here, and this water molecule can come and take the H and alleviate the charge and give us our nice neutral molecule. We can draw those two H's in if we want. We don't have to though. So this mechanism very related to the hydration that we saw. The only thing to really be aware of here is at this step, when we had just added that H on, we will get this carbocation, but it's not stabilized by a second attack. It's actually stabilized through this resonance from the atom that is right next to it with lone pairs. We didn't have that situation for the halogens. They have lone pairs, but they can't make a permanent bond because they'll just be permanently positive. So we didn't have this possibility for the halogens, but we do for oxygen. And so we're going to have that. We're going to get the carbonyl, and then we're going to just have to alleviate the charge to get our product. And so this is how the hydration of alkynes goes.